And here's another example of how to do a physics problem involving Newton's second law, or otherwise known as F equals ma. Let's read the problem. It says a 5 kilogram mass is placed on a frictionless incline, making an angle of 30 degrees with the horizontal. A rope is attached and positioned over a pulley at the top of the incline. A 6 kilogram mass is suspended from the free end. What is the acceleration of the system? All right, after you read a problem like this, you may not really know what's going on, but if you carefully make a drawing of this, it makes a lot more sense. So let's do that. We have an inclined plane. Makes an angle of 30 degrees with the horizontal. On the inclined plane, we place a mass. Let's call that mass 1. And that mass has a mass of 5 kilograms. Okay. Then we attach a rope to that, and there's a pulley at the very end, at the top of the incline, so we position the rope over the pulley, and on the free end, we place another mass. Let's call it mass 2, and that is equal to, I think I said 6 kilograms, yes. All right. And there's no friction between the mass on the incline and the incline itself. No friction at all. Now they ask us, what is the acceleration of this whole system? All right. We're going to assume a direction of acceleration. I'm assuming that this mass is big enough to pull the smaller mass up the incline, and the whole system will accelerate like that. So, indicating that with an arrow, I'm saying that the acceleration will be in this direction. And that will then be considered the positive direction of the motion. Notice that this will be moving up, this will be moving down, but the whole motion of the whole system is considered positive in the direction of acceleration. Now, what if I guessed wrong? What if it's actually in the other direction? What if the real acceleration in the end ends up being that this mass is moving down the incline and this mass gets pulled up? Well, then my answer would be a negative answer, which would indicate to me, oh, I assumed the wrong direction. The direction is actually in the other way. So don't worry about that. If you guess wrong, not a problem. Now the next step is to find all the forces acting on the system, from external sources to the system. So starting with this mass right here, we can say that gravity acts on the system, and so the weight pulling down is equal to m2g. Likewise, gravity also acts on this mass, so we'll have weight pulling down this way, m1g, but since it's on an incline, we then would like to take that force and divide it into its components. One component which is perpendicular to the incline, and the other component which is parallel to the incline. So this can be replaced by these two components. This can be said to be mg1 or m1g times the cosine of the angle theta. This angle theta right here is the same as this angle theta right there. That makes this m1g sine of theta. And so this is no longer there. We've replaced it by its two components. Now there's a second force act down here. It's the incline pushing back. Since the weight of the block m1 is pushing it into the incline, then the incline will have an equal and opposite force, the normal force pushing back. That's according to Newton's third law, and that is equal to m1g cosine of theta. So it's equal in magnitude to this force, just opposite in direction. And of course, those two forces then cancel each other out. And then the only forces left that act on this whole system is this force, m1g sine theta, pulling this down, and m2g pulling this down. Now, if this force is bigger than this, the whole system will accelerate this way. If this force is bigger than this, then the whole system will accelerate this way. The fact that this is a bigger mass, I would assume that it's going to accelerate in that direction. All right, now that we have that, we now grab our equation, F equals ma, and solve it for A. So if we solve it for A, we have A equals F divided by M. And of course, if we work it out this way, this is the net force that we want. What is the net force on the whole system? And we divide that by the total mass of the whole system. Finding the total mass is not hard. We simply add the two masses together. So this is equal to m1 plus m2 in the numerator, I should say denominator. And then to find what's in the numerator, I need to find the two forces, and realizing that this is aiding the assumed acceleration and this is opposing assumed acceleration, so this will be a plus and this will be a minus. So we can write the net force as m2g minus m1g sine theta. All right, now we just have to plug in the values. We could factor out a g. We may make it a little bit simpler by factoring out a g. So this is m2 minus m1 sine of theta times g, and divide the whole thing by m1 plus m2. All right, now let's plug in the numbers. m2 is 6 kilograms. m1 is 5 kilograms. We multiply that times the sine of 30 degrees. And on the whole thing in the numerator, we multiply times 9.8 meters per second square. We divide the whole thing by the sum of the two masses. We have a 5 kilogram and a 6 kilogram mass. So that's 5 kilograms plus 6 kilograms. All right, simplifying this a little bit now. The sine of 30 is 1/2. So this would be 1/2 times 5, which is 2.5 kilograms. So this is equal to 6 kilograms minus 2.5 kilograms. The whole thing multiplied times 9.8 meters per second squared, and then divided by 11 kilograms in the denominator. Okay, now we need a calculator. I can work out the answer here. So we have 6 minus 2.5, that's 3.5, times 9.8, and we divide that by 11, and we get 3.12 meters per second. 3.12 meters per second square, of course. Those are the proper units of acceleration. And of course, since I only gave you the numbers to one significant figures, we should round this off to one significant figure. So we should say 3 meters per second square. Although normally we get the numbers to more significant figures, I just wanted to take it easy here and just use one significant figure in the problem. All right, the next one we're going to do is the same problem, but now we're going to have friction on the incline to see how that changes the problem. All right, stay tuned.